All right. So how you guys doing today? Okay, perfect. All right. So let's start the quick review from the last lecture first. Okay. So if we have some type of the compounds like this, we can treat it with some HCl. Okay. And because of the higher solubility of the carbocation in this form, you're going to have some S1 over here. So the this is the common reaction we can see, but we also try to see this one from the diene too. So not just the one double bond. How about we have a two instead of one? Okay. So we try to change this one to diene. Looks like this. So you have now not just one but two, and we try to do the reaction. And then we find out, oh, there's actually not just one, because you're supposed to see there's this one, okay? So you have this one, so it would be 1, 2, addition. But also we had 1, 4, addition as well. Because you're gonna have those bond, will make move to here, so it can make a carbocation at the end. So the bromine anion will bond to the end. So that makes 1, 2 addition and 1, 4 addition. Sort of the yeah. Go ahead.
What was the process called again? Conjugate compound?
Hmm.
What was the process called again?
Oh, this is called the 1, 2, and 1, 4 addition because the once they have this carbocation over here, right? This bond will move to here. Okay. So that makes those bonds actually not at the center, not at the terminal position, but in the center. That gives the carbocation in the terminal carbons. That's why the bromine and now will come together. So unlike the one we did in organ 1, if we have like a two double bond, like a diene molecule, we have not just the one product, but two, because of the 1, 2 addition or 1, 4 addition. This is what we discussed last time. So quick review, okay? So if that is the thing, there's actually one more thing we need to discuss before we move on to the next topic. So this is the happening more. So if you have two products, now we understand. But this become more major product than this one. So this one become major, this will become minor when it's at the 0 Celsius degree. So very low temperature. This makes the major compound for the 1, 2 addition, the minor products, and the 1, 4 addition over here. Okay. But when you increase the temperature up to 40 Celsius degree, it actually inverts. So at the higher temperature, this will become minor, and this will become major. So there's a reason why this one will become major products at the lower temperature, but become minor product at higher, and vice versa over here. Okay. So this is the one that we're gonna call kinetic control. So if you have two products from this diene products here, we're going to call this the kinetic products. So this is coming from the kinetic control. We're gonna do those kinetic products. But if you're doing something at a very high temperature, we call this thermodynamic control. And then we're gonna call those products thermodynamic products. Okay. So this is about, I think this is about 71% 29, 15, and 85%. But the most important thing is the which one goes major and minor, and what temperature. If it's lower kinetic and kinetic products, if it's at high temperature, it's controlled by thermodynamic control. We call it thermodynamic products here. Okay. So let's try to talk about why is it happening. Okay. That's why. So let's try to say this one. Okay. This is your reactance over here, and then this is your B is your maybe kinetic control or kinetic products. So this is kinetic control, kinetic products. So you get the kinetic control by kinetic control, and you're gonna have a thermodynamic products over here because of the thermodynamic control over here. Okay? So A to the B, A to the C over here. So if that is the case, I will show you some diagram over here. It looks like this. So whenever you're starting with some reactants over here, they're going to experience certain type of energy to proceed in the reactions. If you guys remember this is what we call activation energy. Okay, so activation energy simply means this is the amount of energy they need to have so they can proceed on the reactions. So if they don't have this much of energy, they cannot do the reaction. But if they do have a reaction of this much, they can go proceed in the reactions, and then products at the more stable position, which is a lower position than the position of the reactants over here. Okay, so if that is the case, this is one thing. Let's draw the another one. Okay, let's try to draw another one that looks like this. Okay, so this one and this one has different in activation energy, and also different in their energy difference in reactants and products over here. Okay, so this is reactants, products. So you can consider this one as this small, like activation energy required, but less stable. So if you look at those two products over here, this is the slightly higher position than this one. So even though there's two possible products in this reaction, they're going to have this product is slightly more unstable than this one, because this is higher in energy than this one. Okay, so they will have a very small amount of activation energy to proceed in the reaction, but their product will be slightly bit more unstable than the other one over here, which that actually has very high activation energy is required to happen, but instead they'll have a lower products than the other, so it makes very stable products over there. So when you look at this one, similar curve and just a bit higher products, that is what we do kinetic control over here. Okay. Is more major, and this thermodynamic, this is thermodynamic control. So in these two scenarios, when you have two possible products, thermodynamic control, and here, this will become major and minor in two different scenarios over here. Okay? So let's try to make this more. Let's talk about the kinetic one first. So when you think about the kinetic one, this is happening at the 0 Celsius degree. Okay? So if it's in the kinetic control, they're going to have irreversible reactions. So either they're going to make a major and minor product over here, okay? Major minor product over here. So this is kinetic thermal. Major minor over here. This is only depending on how fast it's happening. Okay? So if you look at this one over here, this one goes to only small amount of energy is required to go forward to make the kinetic products. Okay? But the thermodynamic one has very high activation energy required. So if you're just competing with the speed, this will be faster. Because you only need to go over smaller, like a lower hill to jump over, energy-wise. Makes sense, right? So in this way, if it's kinetically controlled, you're going to have K and T. Let's change it to K and T. Then this reaction will show you in this reaction. So if you go the reaction going forward in this way is a lot faster. So this is, relatively speaking, slower or small. Okay? So in kinetic control, this is why your kinetic product will be your major products. This is much faster to make the kinetic products. But let's change the temperature. Okay, let's change the temperature. So let's change to 40 Celsius degree. So in this case, once again, temperature meaning is available heat energy in the unit volume. So in this case, they don't have much of a energy problem here because you have quite a lot of heat energy available can be transformed into the kinetic energy of their reactants. So they can actually do a bit more easily do the thermodynamic control over here. And also the good thing about this one is they have more stable products. So if they have enough energy, what would they want to make the product is slightly more unstable. They wouldn't want to have because you have a lot of energy, they can actually make not just this one, then they will do it because they can be more stabilized. And also, the interesting about this thermodynamic control is it's actually reversible. Meaning they can also go back and forth like this. Okay. So if you look at this one, I draw the arrow looks like this because it is reversible once again because it has a lot of energy available in this condition because it's a higher temperature. So if you want to go reversible, they actually go this way and this way. Okay. So once you have a very stabilized product from the thermodynamic control, this will have to overcome this much energy to go over. This much, which is really a lot of energy, right? Okay. So this will be very reversible, but very slow. But kinetic one, they can also overcome this easily because a lot of heat once they get to there. But this is slightly unstable. But when they try to go over to reverse reactions, which is possible because you have a lot of heat, it only have to be this much. Right. So in a higher condition, they can actually go once, even though you have a kinetic product made here, we go this way. So it's kind of confusing. I keep saying kinetic product, the thermodynamic control here, but the key point here is at different temperature, you're going to have two products from the nine compounds, but it is going to be one major, the other minor, based on the temperature. If it's a lower temperature, I'll give you an example right here. So let's try to do the actual problem here. Okay? So I just gave you this one over here, right? Let's do this together. It will make more sense now. So we'll have this one. Okay. This is kinetic really control more in the major. It's the major. And then when this one becomes this one, which is will become major at thermodynamic control. So let's do this on this part here. So when they do over there, okay, they're actually going to experience the reaction intermediate. This is where you're going to have your carbocation. Okay? So carbocation, once you have carbon have a positive charge and a double one here, and you have a bromine with a negative charge available for the second step here. Okay? And then you have if it's just at 0 Celsius degree, okay, kinetically control, they're going to be this, okay, in the second step. But thermodynamically will be higher, but yet lower. Okay, so this is 40 Celsius degree. And here, you're going to have a major products. Is you're going to be 1,4 addition product. And here, your major product will be 1, 2 addition here. Okay. I'll explain why. So to make your thermodynamically control and you get the major product will become your 1,4 addition product. Because if you think about this one, these two, can you possibly estimate which one is more stable? So look at so we have a double bond in here and here. That is the major difference in here. And if you look at this one here, this one is in the terminal carbons in here. So if you look at the substitution degree of this double bond, will be just 1. Okay. Over here, you see 3 hydrogens and then 1 R groups attached to this double bond here. But if you can switch the double bond here to here, the good benefit of doing this one is you're going to have this one as 2 R groups and 2 hydrogen. So this is a more substitute than this one. That's why even though it's harder to make, which is require more activation energy, we'll get to the much lower and instead of the thermodynamic products become major. And also it's reversible because a lot of heat. But kinetic can be easily reversed, not so much. So that is why at the high temperature, 1,4 addition product will be abundant. If it's the other way, low temperature kinetic, this only depends on the speed, which only depends on the activation energy, which is much lower, much faster, much easier to make. So in low temperature, they don't have a lot of room for caring about the stability of the product, but the speed. So this will become major in the kinetic control. This will become major products and the thermodynamic control. Kind of makes sense, right? Okay. All right, so let's move on. So just the only thing you really need to remember is the kinetic control. That one with the smaller activation energy will be major. Thermodynamic one is the one that has even larger activation energy, but it's more stable. Then it will be easily overcome those. And the kinetic energy product can be easily reversed. So the thermodynamic product will be abundant at the high temperature. Okay? All right, so but that is the thing. Now we can move on to another type of reaction. We call this the ELs, or the cyclo addition reaction. So Diaz-Alder cycle addition reaction is one type of. This is one type of pericyclic reactions, which will be covered in the chapter 30. But obviously, we're not covering this semester actually. Because when you look at the pericyclic reaction over here, you're gonna learn about how does the p orbital lobe will twist it and bend around to make more like a bigger compounds together. But this is the one type of the pericyclic reaction that we care more because it's quite common in the organic chemistry. So for example, if you have a diene, looks like this, comes into compounds with the double bond. Maybe you have a ethylene over here. What happens to this one is when they come close to each other, they try to put sort of a one single step, like a orbital conjugation. So they will make some sort of a ring, like a semi-ring structure over the hole, like a p orbitals, and then these two are become single bond. So once those are the double bonds, so what actually happened to this one is this one. So you see the one pair of electrons in the p orbital, the pi bonds will go to make the single bond here, and this one pair of electron on the p orbital, the pi, will go to here to make another single bond here too, and this double bond move to here. So overall, you're going to see some cyclic compound. Looks like this. Okay, so this is why we call this Diaz-Alder cycle addition reaction that make very ring structure over here with the one double bond located in the other positions. Okay, so let me give you one more example because the trick is this one. Whenever this is the diene, right? Because you have two double bonds. Okay, diene means two double bonds, right? You have a diene molecule comes into compound that has one double bond, so making some cyclic compounds over here. But the thing is, whenever it does to make this Diaz-Alder cycle addition reactions, we call this dienophile. Meaning they love diene. That's why we just named dienophile. But to be honest, this is not a good dienophile. This is actually poor because most of the good dienophile has a electron withdrawing groups. Okay. So we call this EWG in an acronym. So electron drawing groups, meaning if you have any good carbonyl groups or ester groups or aldehyde groups, they can attract more electron from the double bond groups. That makes even better dienophile. So let me give you some good example. Okay. So it means you only have the hydrogen over here that makes this one not a really good dienophile. This is a very poor one, but it takes very long time to make it happen, or very unreactive, we can say. But so it would be better one would be looks like something like this one. You have a carbon here with the carbonyl groups. Okay, this is like a propanol. Okay. So this is our aldehyde groups with the double bond. So it's a propene, but now it's the aldehyde. But this is our EWG. electron withdrawing groups because of this oxygen here that making double bond to this carbon, this whole carbonyl group with the hydrogen are that groups that makes quite of a the pulling force. They try to attract the electron on those electrons in this double bond in two carbons over here. So why is it so important to make this the very good dienophile is I'll explain here, but let's do this first. Okay, so if that is this one, I'll explain why this is good. Okay? But just let's do this. So if you have a diene comes in again, okay, let's try to do this. Okay. This one, right? Okay, looks like this one. So I'm gonna imply all the hydrogen, you know that, right? By now. Okay, so we just need to do here, right? Here and here. Okay? So you're going to have over here. Okay. So it's a pretty much same. There's the one pair of electron on the p making a single bond in here and here. That's the product here. Okay. But let me explain why is it better when it has some sort of a electron withdrawing groups on the double bond, so they can be better dienophile. Is this one? Whenever you have a diene comes into your dienophile, this will kind of behave like a nucleophile. Okay, and to make this reaction more smoothly happen, then this one has to be in other way, right? Electrophile. So there is the need for the electron from this dienophile will be filled by a nucleophile. To do that, it is better if they have electron withdrawing groups on somewhere in the double bond, so they can be more in need in the electrons, and they will donate the electron to make the two single bond on the top, making a cyclic compound. Kind of makes sense, right? So that is the only thing you have to know for the exam, but I'm gonna briefly explain why it's happening in the molecular orbital theory, but you don't have to know this for exam, so don't worry about it. But I'll just explain for your understanding. So only thing you have to know is what I just told you here, okay? But what is really happening over here is simply this one, okay? So I'm gonna write the 4 p orbitals on here for the diene, okay? Just a second, take some time. Okay, so once again, we're gonna use the so you see there will be 4 p orbital for diene, but only 2 because only have one double bond in the dienophile, right? So I just draw 4 and 2 over here. This is a quick review from the first lecture. This is a wave function we're going to use, the asterisk, which means anti-bonding. This is where we have a lower in energy. So this is in energy, right? Lower in energy. So they're only going to have lined up in the way they can all make easily bond because they're in the same. So just quick review. If you have this one comes into this one, they'll make bond. Okay? If they comes into the other way, there's no bonding there. So there will be means there will be no chance to make a bond here. So best scenario, meaning lowest possible energy you can get is from 4p orbital is this one, because they can be all linked. And the second best is they have 2 bonds in the side, but just one node. So I can show you here. So they can be linked in here, but here is a different, right? Dark, white, dark. So this node here, but these 2 can do here. And then another one you can do is here. You can do so they can be one here, but on the side it's different, so there'll be not. So in this one has one node. This one has two, 1, 2. And this one, the worst possible scenario would be obviously this one. They all cancel them each other. So there'll be 3 nodes. Meaning the highest energy level required. Okay? So obviously to make a bond, they always want to make a bond in these two. That makes those the two, each electron in the double bond makes in here and here. Okay? And then for this one, obviously at the bottom, they need to be linked one first, and another one here, which is one node here. So in here, they shouldn't be no. So we make bond in this form, not this one, because there will be one node. This is where they cannot make a bond, which is okay because they only have to have a one pair of electron making a p here. If that is the case, you actually coming into this part is what I told you, electrophile. And this will become your nucleophile. So nucleophile is looking for something that need electron. So this is where you're going to use this electron, not here, because they need to have the electrons here. They're going to give us the electron in the bonds. Okay? Then they need to have a highest occupied molecular orbitals. You guys remember this in GenChem 2? Highest. So okay. There's 4 levels over here, right? 4 levels in here. There's 4 possible scenario. Most stable, second unstable, most unstable. Okay? So there's 4 possible electron can be filled. For each is 2, because it's orbital 32, up spin, down spin. You remember this, right? But obviously, to make a really good conjugate compound here, have only 4 electrons, 1 pair for this one and this one, has to be filled down, down, and there's no electron here. So they can be very strongly bound. Right? Okay. For this one, double bond only can make under this one, because there's no node, the 2 will be bound in the same side, same lobe of the P. So it'll be down, there'll be nothing over here. So when you look at the nucleophile, this is the one that will give you the electron. So for nucleophile, you need to find the highest level that filled with the electron. So these will not count. So this is the highest level, but we will not count because there's no electron here. Because we're looking for HOMO, meaning the highest occupied molecular orbital, which is this one. So among these two, this is higher, right? So this is our HMO. With the levels in the field of the electron, this is the highest one, right? I know this is the highest, but there's no electron there. And they need to have electron to donate the electron to make a bond because it's nucleophile. Makes sense, right? Okay. But now this one behave like an electrophile, meaning they need to have electron. So they can choose this one highest because it's already filled with electron. So they choose lowest unoccupied orbital, molecular orbital. So we call it LUMO, lowest unoccupied molecular orbital, which is what? Here. Because this is filled with electron, but this is not. Okay? So when those two combination comes into here, so I'm sorry, it's very awkward drawing. But usually NuMO is slightly higher. So if you do this one, those electrons will be shared in here. So they can make a single bond here at the bottom. Okay? So that's why they make the bond here. So it happens when those happen, in the loaf. So it happens when those two, so this is two double bond, right? Okay, but second highest is the one that has the one lower and darker in the case. And whenever you have this one, there's also two p over here, which should be different in the position of the loaf, plus minus loaf, which if that match up with here, like this, then it works. So they can make a bond here, which is a single bond. Okay? Kind of makes sense. But the only thing you have to know really is the diene will kind of behave like a nucleophile. And the dienophile will be electron pull groups, electrophile. That's all you need to know. But this will actually kind of make you better understanding of why is that one. Okay. Kind of makes sense, right? Kind of okay. So if that is the case, let's do just one more, and I'll stop here because we. Anyway, so whenever there's one more thing I want to tell you is this one. So we have another dienophile with some. This is maybe method groups. This one has with also carbonyl groups with even other oxygen. So we'll make very good ether group on those. Ester group on this dienophile. So in this case, this is a double bond. So you can also do this one same, pretty much the same. Okay. So you can have here. So they can make here, right? Because you see now that it works, right? And then they're going to be on this position. And this one as well. But once we had this double bond, this is, you guys can see, is in the cis, right? The Z configuration here, Z. Then that makes also so there's a hydrogen over here, right? And this one become dash. So this also makes, because they're bound in the same side, hydrogen, and those are the groups that makes the cis products. Because when they're coming into this plant, as you saw that they're all on the same side. So whenever combined to make the one cyclic compound in this part, those two and two will be also in the same side as well. So we call this cis products. Okay. So what can I say now? Maybe you put it a trans now. It only changed so this is maybe trans now. Okay, E confirmation here. The only thing you have to do, this will be trans, right? Product. So you need to switch the position. Because now you have the groups will heading back of this board. This is coming front. And also hydrogen as well on the fronting up, and this hydrogen pointing back. So all in the trans position. So this will be determined either you're going to have a cis or a trans product, where you have a dienophile in the trans, or E and Z you can say, on those position. So you can keep it on those all groups once you make the cyclic compounds in the product, cis and trans. Kind of makes sense, right? Because they were coming in the different sides. So they're here, same side, same side. Okay. So I'll just stop here today. I'll just give you